Welcome to Brain Vision.
This is chapter 27, problem number 72. We have a bar given to us on our coordinate system, extends from a point A towards a point B. In the background, we have magnetic field that is into the board. Goes like this. So in part A, we are asked to calculate the current passing through this bar if there is rotational equilibrium, which means the net torque on the bar is going to be equal to 0, when the angle with the horizontal theta is 30 degrees. So we are to calculate the current. Let me remind you that there is magnetic force and gravitational force acting on the bar. So the gravitational force is always going to be down, right, along negative y direction Fg. And then this is going to generate a torque that would rotate the bar around the axis clockwise, right? So that's what the gravitational force would do. Then, if we want the rotational equilibrium, we have to have a force that is actually forcing the bar to move counterclockwise so that they can balance each other out. So from this logic, you can't actually simply say that let's say we're trying to determine the direction of F sub B, but we know F sub B should be along a particular direction so that it would cause the bar to rotate counterclockwise because it needs to oppose to what the gravitational force does. So in order to achieve this, let's imagine two different scenarios. Let's assume that the current is going from B to A. Okay, the current is down. Then given the external magnetic field, what would be the direction of the magnetic force? The direction of the magnetic force would be something going through the center, assuming something like this, F sub B. This would also generate a clockwise rotation so that we can never achieve the rotational equilibrium. So then it cannot be, right? So then actually, on the contrary, the direction of the current on the wire has to be from point A towards B, so that using the right-hand rule, we can show the direction of the F sub B to be along this particular direction. Then it would cause this counterclockwise rotation. So from the get-go, we actually answered part B. Part B was asking what the direction of the current should be. So the direction of the current should be from A to B if we want rotational equilibrium. Now, the net torque has to be equal to 0. Again, in the problem, we are told to take the previous problem as a reference. So in the previous problem that we worked on, problem number 70, we had derived this the torque generated by the magnetic field to be, for a bar like this, L squared B over 2. So this would be the torque generated by the magnetic field. And now let's calculate the torque generated by the gravitational field. Then it's going to be equal to F sub G, right, times the distance from the pivot point to the point where the force is applied, which is L over 2. And now we have to figure out the angle between F sub G and the R vector. Sorry, R and the F sub G vector, right? So if we do that, let's show the direction of R. Direction of R is along this particular direction. F sub G is down. I have to carry here to find the total angle between the two. So it's actually 30 plus 90 from here, right? The angle then is 30 plus 90. So it's 120 degrees. Then, again, this torque is forcing the bar to rotate counterclockwise. The other one is forcing it to rotate towards clockwise direction. Then net torque equals 0. That means IL squared B over 2 minus MGL sine theta over 2 is going to have to be 0. From that, IL squared B over 2 equals mgl sine theta over 2, because they're going to cancel. L and L is going to cancel. So then if you isolate I out of this equation, I is going to be mg sine theta over el. Again, this theta being 120 degrees. So when we plug in the values for I, then what we get is 0.012 kilogram. This is the weight. Sorry, this is the mass of the bar. 9.8 being G meters per second squared, sine 120 degrees over the magnitude of the magnetic field, 0.15 Tesla, times the length, L, right? The length of the wire is 30 centimeters, which makes 0.3 meters. So when we plug everything in, we find the current to be 2.26 amps. And again, this current has to go through from point A towards B for the rotational equilibrium to be preserved.